All right. So today we're going to start talking about chapter 2, starting off with section 2.1. But before we really get into things, I want to talk about a couple of different ideas. To start off with the secant line. Does anybody know what a secant line is? For curiosity? So the word secant is derived from the Latin word for to cut. So a secant line is going to do something about cutting a graph, right? Or a curve or something. That would make sense, right? That's where the word's derived from. What a secant line is a line that intersects a curve in at least two different places. So to show some of this, let's draw it out on the board. All right, so let's imagine we've got a curve. It looks something like this. Everybody at home, how well can you see the board?
Pretty well.
Awesome. Better than what it's been being?
Yeah.
All right. So we're going to say that this curve is a function. We'll talk about why in just a second. Why I want to designate it to represent a function. Now we're going to have three different lines intersecting this function. We want to determine which one's going to be a secant line. The first line is going to look something like this. The second line is going to look something like this. The third line, like this. Of these three lines, which are secant lines based on this definition up here? 1 and 2. Who agrees? Why isn't 3 a secant line?
Because it only crosses once.
Right. How do we know it only crosses once, though?
Because we can see it on the board.
Say what?
Because we can see it on the board.
Well, there's that, but if this line, if this curve didn't represent the graph of a function, there's a possibility that it could wrap back in on itself, right? So if this wasn't a function, we can imagine someplace way off in the distance where it turns back around and sneaks up underneath like this, right? So we know that this line, L3, only crosses the orange line once because it's a function. Make sense what I mean? That's why I want to go ahead and designate this as a function. Now, having said that, this brings up a particularly important point, right? Notice I designated this as a function. And I didn't explain why in advance. The reason why is because as we move through this class, there are going to be times that you're going to be able to, or you're going to need to look at something like a function and know its properties to understand why a thing is happening the way it is. Make sense what I mean? Yeah. So by designating this a function, we knew it didn't wrap back around. That's why it was important. So, all of this is well and good, but how would we draw? How would we derive the line, or the equation for a secant line? What I'm asking is, got a function. With a secant line. All right, so we've got this function, the blue graph, right? We've got this secant line that crosses our function in at least two places. What's the equation for that line?
Secant slope, secant and the slope of the line.
Not quite, but you're on the right track. What we're going to do here is we're going to apply point slope formula, right? We're going to say, all right, this line is going to be equal to y minus our function at some x value is equal to its slope times x minus that x naught value. Everybody agree? Now m here m we understand to be the slope. M is going to be equal to f of b minus f of a, all divided by b minus a. Everybody agree? All right. So let me erase some of this really quick. Make some more room here. Now looking at this graph, I want you to notice something. From A to B, we cross a distance of delta x, right? So what I mean to say is this length is equal to delta x. Agreed? So using this, we can rewrite b then as a plus delta x, right? Agreed? So the slope here, we can rewrite. What we do, we're going to get f of x plus delta x minus, my bad, a. Minus f of a divided by a plus delta x minus a, which is all going to come out to be f of a plus delta x minus f of a delta x. Looks familiar, doesn't it? It should. Shows up in our homework a lot, or at least it has lately. That's a hint that we're going to be doing something with this in a little bit. Now notice what this gives us. what this gives us, all in all, is the line for this secant, or I mean the equation for the secant line, right? The change in y is represented as f of x plus delta x minus f of x. The change in x is represented as delta x. So that's going to be our slope, right? And point slope formula is going to give us the equation of that line. Now, what happens if we bring in b? What happens if we take the point x equal to b and move it closer to a? What would happen to all of this up here?
Your secant line would get more narrow.
In the sense of the word, yeah, like it changes the secant line in the sense that in our example here, it's going to get more and more flat up to a point, and then it's going to start kind of reversing back, right? It's going to approach a slope of 0, and then approach a negative slope. Agreed? Okay. Well, what happens then? Well, equation of the secant line we've already gone over. What happens now if we let this delta x go to 0? What are we describing when we say that?
Would just be a point along the function.
Say what?
Would it be a point along the function?
Yeah. If delta x goes to 0, then b goes to a, right? Because b is just going to be a plus delta x. So this delta x thing is going to 0. B has to be going to a. Is everybody cool with this? So we're talking about a limit here, right? In particular, we're asking the question, what is this slope? Make sense what I mean? So looking at this, what we're describing is this example where delta x consistently gets smaller and smaller and smaller. But notice when b eventually reaches a, or when delta x eventually reaches 0, we're not a secant line anymore. Because we don't go through more than 2 points. Or I mean 2 or more points, I should say. Right? So this line now only goes through 1 point of our curve. So it's not a secant line anymore. Instead, it's what's called a tangent line. Tangent, for whatever it's worth, comes from the Latin word to touch. And if we look at this picture, it makes sense, right? We only touch our graph at one spot. So what is a tangent line? A tangent line is a line that it touches your graph at one point, and in a small little neighborhood about that point, so in the immediate vicinity of that point, our graph, our curve, and the tangent line look to have about the same slope. They look almost parallel immediately around that point. Does this make sense to everybody? kind of, sort of. So as a couple examples, we've got each of these tangent lines and their points P. You look right around that point P in all three of these graphs, our function looks a lot like that line, doesn't it? Like you can't tell the difference between the graph of our function and our tangent line when it's really close to P. Does that make sense what I mean? So in that sense, we're approximately parallel, you could say. It's not technically correct, but it gets a sense across of what we're trying to say. A couple more examples of tangent lines. Notice we don't have to be talking about a function to have a tangent line, right? Circles aren't functions. So that has a tangent line. And again, we look really close to this point. It looks like the circle and the tangent line are approximately the same. They're approximately parallel. So one way to view what I'm talking about with this limit is to check out this awesome GIF that I made for everybody. So in this GIF, it's not GIF, argue with me and I fail you. In this GIF, instead of using delta x, we have h. And as h approaches 0, this point is going to move up, right? So here we're saying a minus h. Up above, we're saying a plus h. In either case, as h approaches 0, both of these points will approach a. Agreed? And both of these secant lines then will approach this tangent line. So to show that again, so what this limit is effectively doing is moving your secant line into a tangent line. Does that make sense what I mean? This thing gives us the definition for the slope of a graph. For any function f of x, the slope of its tangent line is given by this is given by this equation. And we also say that this is the slope of our function. Now, some people would cringe at saying this is the slope of a function because in general, slope is for lines, not for curves. But we can think of it in the immediate vicinity of that point. The line, the curve, looks approximately straight. And in that way, it's the slope of our function. Does that make sense what I mean? Like if you were to zoom in on a circle, eventually that edge looks like it's straight. And in the vicinity of one of those points, we would say that that function, that circle has a slope according to this equation. Everybody with me? Yeah. Cool. So how are we going to use it? Well, start off with an example. The function f of x is equal to x squared. I want to know what the slope of it is at the point negative 2, 4. Well, we know that the equation is going to be this crazy thing, right? We replace a with negative 2. We're going to just work through the algebra. The first thing we're going to want to do is actually calculate what this f of x plus delta x plus blah, 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 all of this is. We're going to want to expand all of that out. Then we're going to want to try and do our best to simplify our denominator and our numerator. And then we're going to try to factor things out, cancel out, until eventually we get to something we can calculate the limit for. Once we've done all of that, we apply the limit, and we get negative 4. Pretty straightforward, right? You're just doing the algebra. You're massaging it, then you're applying the limit. And all of this is to find the slope of our function at this point. The tangent line of this function is going to be this line. Again, notice that right around that point, you can't distinguish the difference between the tangent line and our function. This is a common property, a common thing to see come up time and time again when talking about tangent lines. Now, having said all of this, what's the equation of that tangent line? Any thoughts? All right, so because this is going to be a common question to ask, I will most certainly at some point ask you all this. I want to make sure that before I do, you'll know how to do this. To find the equation of a tangent line, the first thing we want to do is determine what point we want it to touch of our original point, right? In this case, we want to go and touch the point negative 2 is equal to x, right? So that's going to give us negative 2, 4 as a point. After we found the point, we want to find the slope at that point. That's what we've done here. Agreed? So n is going to be equal to negative 4. Now we're going to use point slope formula to figure out what the line of the tangent is. I mean, the equation of the tangent line is. Now we're going to just really plug everything in to the point slope formula. Rearrange some terms. Simplify it as much as we can. And that's going to give us the equation for our line. So let's do that really quick. We know that f evaluated at negative 2 is going to be 4. We know our slope is negative 4. we know that our x is -2. So let's try to simplify some of this. Going ahead and just making that negative, or the minus -2, making it addition. Then we're going to end up with y minus 4 is equal to -4x minus 8 . Or y is equal to -4x minus 4. So all we're doing here is applying point slope formula after we found the slope. Make sense? Yep. So what if we don't want to find it at a point? What if we want to find the slope for all points? So generate a generic equation that'll give us the slope of our function no matter what point we put into it. How would we do that? First, I want y'all to check it out. This is just going to be a line, right? So we know the slope is going to be -2 here. That's what we should expect anyhow. Looking at the graph, it's just -2, okay? Now, the way this works is instead of plugging in a particular value for this x, we're just going to leave it as x and calculate all the way through until we apply the limit. Does that make sense what I mean? So instead of putting in a particular x value, we're just going to leave x there. We're going to run through the math the exact same way. So to see what this looks like, it's another example. So here we got the parabola, right? We want to find, well, let me actually go on to the next slide and then I'll come back to this idea. Because I think I touch on it in like 2 more slides. Exactly what I'm asking, right? How do we find the general equation for the slope of a graph at every point of our function? Just like that last problem asked. I do ask. Cool. How do we do this? So imagine, just because this question already does it, we want to find the slope of our function at 2 different points. It would suck to have to go through that entire long process twice, right? So it'd be nice to have an equation that we can just plug in our points and be like, all right, give us the answer. Like, let's get to it, right? Make sense what I mean? So how would we do this? Well, like I said, we would go through the entire process, except instead of plugging in one of these x values, we just leave x, get to the very end, and then plug in our x values. Does that make sense? So I can already tell you that the generic equation here is going to be 2x. But having said that, let's look through all of this. Let's actually do it. F of x plus delta x minus f of x over delta x, apply the limit. This is going to come out to be the limit delta x going to 0 of x plus delta x quantity squared plus 1 minus x squared plus 1 all divided by delta x. So let's expand this out. And then we'll drop the square parentheses right after that. Limit delta x goes to 0. It's going to give us x squared plus 2x delta x plus delta x squared minus x squared plus 1, all of that inside parentheses, divided by delta x. Now here, we're going to drop our square parentheses. Well, first we're going to distribute the negative through and then drop. Make sense? So doing that, you're going to get limit as delta x goes to 0 of x squared plus 2x delta x plus delta x squared plus 1. I forgot the 1 over here. Plus negative x squared minus 1. Because all I've done is distribute that negative through, right? All this divided by delta x. Holy shit, this is taking forever. Take a bathroom break, eat some chips, watch your favorite TV show, come back, pick it back up. We're going to drop the parentheses now. We're going to get x squared plus 2x delta x plus delta x squared plus 1 minus x squared minus 1 all divided by delta x. At this point, we all hate Newton and Leibniz. But we're getting close. Because now, we've got some cancellations. This x squared with this x squared. The 1 with the 1. getting close now. Because now we've got the limit as delta x goes to 0 of 2x delta x plus delta x squared all divided by delta x. This looks a hell of a lot better now. So now we're going to factor out this delta x from both terms. Agreed? We're going to have the limit as delta x goes to 0 of the quantity 2x plus delta x times delta x divide delta x. Check it out, these delta x's are going to cancel. What we're going to be left with now is going to be the limit as delta x goes to 0 of 2x plus delta x. That's a polynomial. We can just apply the limit directly to it, right? And when we do, we're going to get 2x. So I was able to look at this and tell you what it was. Why? How can I look at this and know what this is? Because there's going to be some rules and some properties we're going to talk about later. But before we get there, we're going to do this by hand so many times until you're going to hate me. You're going to think I'm a sadist. I'm going to love it because I know it's going to torture the hell out of you. But when we get to those rules and properties, you're actually going to want to learn them. You're going to want to know them because you don't want to do this ever again. So just know in advance, your homework, I'm going to give you problems like these. Probably going to have 20 or so. You're going to do it so many times until you're going to want to choke me. Like you are all going to get together and look into buying an assassin. But the reason why is so that when we get to the other side of all of this, it becomes that much easier. Make sense? All right, so we've got this 2x. We've only done half the problem though, right? Now we have to plug in -1. And we have to plug in 2. So I'm just going to jump. Looking at this, we've got the tangent lines at these 2 points. Again, check it out. Inside of this small little neighborhood, right? Our tangent line looks a lot like our function. What we mean when we say that this is the slope of your graph. It's really the slope of your tangent line, but your tangent line is so similar to your graph immediately around this point. So we just go ahead and say, yeah, it's the slope of the graph there too. Make sense? Finishing up this problem, we go through all the math, get to 2x, and we just plug in -1, and we plug in 4. this thing that I keep talking about, this is the definition of a derivative. The derivative in a intuitive sense can be interpreted as the rate of growth of your function. It tells you how y changes with respect to x. And in that way, it can be thought of the slope of a function at a point. A function is differentiable at a point x if the derivative exists at x. And when we take the derivative, we call it differentiation. So I haven't posted these yet. I'm going to wait and give you all a couple seconds to write some of this down. That was hot. That was still hot.
You said it could be called the rate of growth of a function.
It can be considered that, yes. Because what we're doing is we're comparing the way we change in the y direction as we change in the x direction, but that change in the x direction is minuscule. It's an infinitesimal, is what we call it. All right, I'm gonna jump to the next slide. So, some notation, everybody's favorite. Different ways we might write the derivative, or we might represent it. Because, let's be real, it would suck to write this every other line. So instead, we use abbreviated notation, and it looks like this. Some of them look like this. Hey, check it out. There's that prime I was talking about the first day of class. When I said that that prime was going to have another meaning later on, this is what I was referring to. What time is it? We got 4 minutes and 6 slides. We can do that. We can go through 6 slides in 4 minutes. So let's say we wanted to find the derivative of this function, 3x squared minus 2x. Without looking at everything down here, this is going to come out to be 6x minus 3. Again, cheating. My bad, 6x minus 2. But I'm cheating. There's a trick to this that we'll talk about later on. Until we get there, though, have fun. So all we're going to do here is we're going to say, let's find f prime of x, the derivative. To do that, we're going to replace x with x plus delta x minus f of x, right? Divided by delta x. Substitute all of that in, expand all of it out. Take a break. Simplify. Factor out and reduce. Factor out and simplify again. Excuse me. And then reapply the limit. Cool with everybody? All right. Well, with 2 minutes left in an entire other problem, I think I'm gonna let y'all go. If y'all have any questions, I'll stick around for a couple minutes. Feel free to ask.